Folks, in subsequent sections we're going to learn how to solve a system of ordinary differential equations, and we're going to do that by representing that system as a matrix equation that we then work on solving. In most of the cases we deal with, we'll be considering only linear first-ordered systems of homogeneous differential equations, but in some cases we will do some nonlinear, and we will look at a few non-homogeneous systems like the one that we have here. But before we get into solving these using the techniques that we've started developing already, we want to learn how to represent these systems of differential equations as a matrix equation. So let's just look at this system of differential equations here. Notice that we have two unknown functions. And this is, we saw this at the very beginning of class, we haven't seen it since then. We have two unknown functions, and what are they? Well, we've got x1 of t is one of the unknown functions, and x2 of t is the other unknown function. And we've got this tied system, sometimes this is called a coupled system, where dx dt, dx1 dt is given in terms of the sum of these two functions plus this non-homogeneous term here, and dx2 dt is given as an expression involving, in this case, 3 times x1 of t plus this non-homogeneous term here. So what we'd like to do is we'd like to learn how to represent this as a matrix equation. So the first thing we're going to do is we're going to represent our unknown functions as a single vector, and we'll call that vector capital X. Sometimes you might see it written just as X bar. This way, I think I'll use a capital X in most cases. So we'll write capital X, and a capital X is going to stand for x1, x2, the two unknown functions. Sometimes when it's necessary, we'll write a little more detail there. We'll write x1 of t and x2 of t. Okay. Well, if you've had Calc 3, you've learned that to take the derivative of a vector valued function, you simply take the derivative component-wise. And so if we want to represent the derivative of this unknown vector valued function, we could go ahead and write it as x prime, and we simply take the derivatives component-wise. So we take the derivative of the first component of this vector, and we take the derivative of the second component of this vector. And if we wanted to show more detail, we write x1 of t prime and x2 of t prime. And then we can go ahead and actually, we're now ready to represent the left-hand side of this matrix equation as just x prime. We might also sometimes write x prime of t if we want to emphasize the independent variable t. So the next thing we're going to do is let's represent the homogeneous component of this matrix equation. And so what we're going to do is we're just going to say that this is going to be some coefficient matrix. In this case, it'll be coefficient matrix because this is a linear system of ODEs of constant values for the coefficient function. So we'll go ahead and represent it this way, where A is the matrix 4, 2, 3, 0. And then we're going to add to that the two non-homogeneous terms. Well, in this case, the first non-homogeneous term is a e to the minus t times the function. In this case, there's only one e to the minus t, and that's in the first equation, so we get 2, 0 for that entry. And we've got an e to the t, and that only shows up with a coefficient of 1 in the second equation, so we'll represent it with a 0 for the first component and a 1 for the second. Okay. So that's one way we could represent this. I'm going to go ahead and take it one more step. Let's actually plug in what that matrix A is just to make sure we're all on the same page. The matrix A we said was 4, 2, 3, 0 times the unknown function vector x plus e to the minus t times 2, 0 plus e to the t times 0, 1. And notice if you expand this thing out and then equate it component-wise, this is x1 prime, x2 prime is equal to 4, 2, 3, 0, x1, x2 plus e to the minus t, 2, 0 plus e to the t 0, 1. And you can see that if we went ahead and actually did the matrix multiplication here, and then we added component-wise, we'd be back at our original system of differential equations. But this is how we're going to represent that entire system as just a single matrix equation. So we'll practice that in the next example, and then we'll move on to some additional examples later on in the document.